Hey everybody, so in this video we're going to do a quick continuation of infinite limits before moving on to concepts like derivatives and integrals, which you'll learn later on. So this is a slightly more complex infinite limit problem than you saw in the last video, right? So to quickly recap what was shown in the last video, we covered what infinite limits are and kind of basic limits with given equations, right? So maybe you might have x to the 5th power divided by 4x to the 4th. So how do we evaluate an infinite limit for this? Well, that's pretty basic because you can just cancel out your common x's. Or if you just have, maybe x plus 5, the limit of this is x approaches infinity. Well, you don't even need to cancel out the x's in this scenario, and you can just go ahead and plug it in. So we're going to cover a scenario where you can't really, or it'll take a lot more time to cancel it out, or you just can't cancel it out. And we're going to use a method that is called long division, right? So this is basically, it's not a new concept per se, but we're going to use long division. If you remember pretty far back in maybe elementary school, you used to do division more like this, using something that looked like the square root symbol to do division, and you'd get your answer doing it that way because you'd multiply the numbers, calculate the sums, and so on. So we're going to use that method to solve this limit. And we have to set up what our division process is going to be. So this becomes x cubed plus 1 divided by x minus 1. Now here's a key tip to use during long division processes. So whenever you're setting up long division, make sure you have all your x's in the proper position. So to kind of explain what that means, right? Over here we have a cubic function, which means we're missing at least two terms. We're missing two terms in this case. So let's go ahead and fill out what those two terms would be. We have x cubed, but there's no x squared, so we'll just add in a 0x squared, a 0x. So now that we have this, it becomes a lot easier to keep track of which x's match up with which x's due to the degrees that can be different. And we can go ahead and start our long division. So to get x cubed from x, you'd have to multiply by x squared. And now you subtract x cubed minus x squared. Now this is why I said you should write it fully out like this, because if you were to subtract x squared from here, you might end up writing the wrong value for your x squared, or you might end up confusing it and making this a 1 minus x squared, which is not correct. So we'll go ahead and cancel these out, x cubed minus x cubed, and you're going to get a minus negative x squared, which gets you a positive x squared. So you're going to have positive x squared plus 0x plus 1. Now continuing the process, we'll get plus x. And once again, we'll subtract. Well, multiplying x times x minus 1 gets you x squared minus x. So that'll cancel out the x squareds, and you'll get a positive x plus 1. Now, you can divide this one more time because x goes into x itself once. And you subtract a x minus 1. The x minus x cancels out. You get a 1 minus a negative 1, which is 2. So this becomes your remainder. Now, what does that mean for the limit? Well, we can now rewrite this limit to be the limit as x approaches infinity of, we have x squared, right? So let's like this in multiple terms. So we'll have x squared plus x plus 1, right? This times x minus 1, right? Because we have x cubed plus 1 over x minus 1, or divided by x minus 1 gets you this, and this plus 2 divided by x minus 1. So this is what term we have now. Well, how do we evaluate this infinite limit? At this point, you can cancel out and start plugging in things. Plugging in infinity into this term here gets you 2 over infinity, which can be evaluated to 0. And plugging in infinity over here, well, it's just a bunch of x's that are being multiplied, and you'll end up with some cubic, so you should get infinity. This becomes infinity plus 0. That 0 is just some random, well, not random, but that 0 is just a value that doesn't contribute to the numerical value of this infinity. And for that reason, this limit can be evaluated to be infinity. So this should give you a basic idea of how complex infinite limits problems can get, especially with long division. You might have, a quartic or even a x to the fifth term here that you're dividing, and it can be a lot longer. So you have to keep track. And once again, use this kind of idea here to keep track of all your x values. It makes long division a lot easier. So hopefully you've got a pretty solid grasp of what infinite limits are. Now, we'll talk about infinite limits once again when we start discussing trigonometric limits, such as, like I mentioned in the previous video, the limit as x approaches infinity of cosine x or sine x, right? You can't use the same methods we're using over here because these sine and cosine functions or trig functions are usually constantly fluctuating like that. So, as x approaches infinity, you can't really determine just by looking at the graph which value it'll approach. So we'll use some other methods to determine how to solve trig limits, and we'll come back to that. Hopefully, starting in the next couple of videos, we can start going over new things, new topics such as derivatives, and we can maybe try to fit in a limits review to cover most of the concepts we've learned.